Welcome to the third lecture on iterative compression, and the third lecture will be about branching in composition. So, based on how much time we have, we will definitely look at an algorithm for feedback vertex set in undirected graph, FVF in undirected graph, and if we will have time, we will look at ThreeHitting set. Okay. But let us try to do feedback vertex set in undirected graph, and this is about how we can do branching in compression. Okay. So, recall we are going to solve what problem? We are going to solve disjoint compression FVS, right? Disjoint compression FVS. So, input is going to be G, an integer k, set W. What is the property of set W? G minus W is acyclic and W has size k plus 1. My parameter, right? My parameter is okay. My parameter is k, and the question we are going to look is whether there exists a set F subset of Vg first has size k, G minus F is a forest, and third F intersection W is empty. So, we are looking to test whether there exists a feedback vertex set whose intersection with the given feedback vertex set of size k plus 1 is disjoint or not. Okay. So, as before, let us apply our sanity reduction rule. So, what is our sanity reduction rule? So, our sanity reduction rule is if graph induced on W has a cycle, return no, right. So, if we are trying to find a feedback vertex set or a set which intersects all the cycles and graph induced on W has a cycle, it means there is absolutely no way we can hit this cycle by a vertex which is not a W vertex. Okay. So, in that case we can immediately return no. So, the world of our world looks like W, okay, and this is my forest, right. This is G minus W, which is a let us call it H is a forest, and I have drawn forest for you. Okay. So, there are some reduction rule that we could apply immediately. So, we will first apply some reduction rule. So, from now onwards, first of all assume that graph induced on W has no cycle. Okay. Now, so first reduction rule that we will apply, rule 1, if there is a vertex of degree at most 1, right. If there is a vertex of degree at most 1 in G, delete it. Okay. Now, rule 2, okay. If there exists a vertex x in H such that graph induced on W union X has a cycle, then what will we do? G minus X W k minus 1, okay, right. Then we delete X, remain W. Why? Because what is this lemma tells? What is this reduction rule tells us? That look, here is a cycle, we know that W has no cycle, right? Graph induced on W. So what is the reduction rule 2? It's exactly the way we have been doing for this triangle thing, that look, if there is a cycle that contains exactly one vertex which is not in W, then we must pick that vertex W, right? So what we know, that look at this GW, this is W which is colored, and I have a vertex X. This is acyclic, right? But the moment I add X, it has a cycle. What is the meaning of this? There exists a cycle which is of the following nature, right? So from this cycle, the only vertex that do not belong to W is X. So we selected X into our solution and decrease the parameter. Right? So if you notice, we have been applying these kind of reduction rules for feedback vertex set of tournament also, right? Where we had that, look, if there exists a triangle where two vertices of that triangle belongs to the forbidden set, then the third vertex must belong to the set we are going to construct. Okay. So final, we have a reduction rule 3. So what is the rule 3? If there is a vertex, V in vertex set of H, okay, of degree 2 in G, if there is a vertex V which belongs to vertex set of H, but it has degree 2 in G. So you must have seen degree 0, 1, 2 reduction rules to make a graph degree at least 3 in your lecture on kernelization, or not kernelization, but in the branching algorithm, where you would have seen for feedback vertex set, you have previously seen this, right? Previously seen this 2k plus 1 to the power k n to the power big O of 1 time algorithm, right? So in that you must have seen these reduction rules. So we will try to make a similar degree 2 reduction rule, okay? Okay. If there is a vertex V in V of H of degree 2 in G, such that, okay, so at least one neighbor of V, at least one neighbor of V is in V in G, is from vertex set of H. So it is not that, you know, I have a degree, like I have a vertex of degree 2 where both his neighbors are in like in W, but there is at least one neighbor which is in V of H, okay. Then delete the vertex V, okay, and make the neighbors adjacent, okay, even if they were adjacent before, okay. So this might lead to multi edges, okay. Graph may became multi edge, okay. So what is this reduction rule? So basically what it tells us that, look, first of all, I am only going to look at those vertices of degree 2, okay. So look at a degree 2 vertex here. How can his neighbors are? His neighbors could be, where are his degree 2 neighbors? His degree 2 neighbors could be this, or this vertex could be both of his degree neighbors are here, okay, or this vertex, right, could have a degree here, here. Okay, this is not right. So, what I wanted to draw is like it could be like this. Okay. So, what is our reduction rule tells us that look, if you have something of this nature where both of its neighbors, right, where both of its neighbors, right, both neighbors in W don't do anything. Both neighbors in H, then what will we do? What is the reduction rule we will do here? Well, here the vertex. So, we will just make this guy this. So, suppose this is A, B, C, here is an A and C, delete B. Okay. Now, suppose let us call it, you give me a name, say X, Y and J. If you have Y such that there is one vertex in Y, other in Z, so what will you do? You will make X and Z neighbor and by deleting Y. It could have been, so for example, our situation could have been that X is there, Y is there and Z is there and there is an edge here. But then your reduction rule would do, right, X and Z there is an edge. So, this is what it says that if you have a degree 2 vertex in graph G, so these are vertices of degree 2 in graph G such that at least one neighbor is in H, then we will apply this following short circuit operation, delete this degree 2 vertex and add an edge between both of its neighbors, even if there was an edge before, you make it a multi edge. Okay. So, this is what you do degree 1, degree 2. Okay. So, what is our algorithm does? Our algorithm is very simple, right. Algorithm is very simple, applies rule 1, rule 2 and rule 3 as long as applicable. Okay, as long as applicable. So, applies rule 1, 2 and 3 as long as applicable. Okay. Now, at any stage, if k is less than 0 and G has a cycle, what will we do? We will say return no. Right. So, for now let us assume that we have an instance Z W k, k is greater than 0. Okay. Okay. K is GWK, k is greater than 0, strictly greater than 0, no and no rule 1, 2 and 3 apply. Now, we will apply a very novel branching rule. So, our idea is very simple, novel branching rule. Okay. Okay. So, let us look at our world again. Okay. Let us look at our world again. Look, I have not proved the soundness of reduction rule 1, 2 and 3, but they are just obvious, right. So, they, like similarly, like for example, why they are obvious, look, if you, why do you need to pick Y? Because every cycle that do pass through Y here, every cycle that do pass through Y, every cycle that do pass through Y also passes through X and Z. And although X is not allowed to be picked, you can pick Z into your solution, right. Similarly, you can delete B and every cycle that passes through B also passes through A and C. So, in the replacement solution, and the reason why I cannot apply reduction rule here, because look, it's both neighbors are in W, but and both are forbidden. So, if I say that okay, let us put an edge and look at a solution where we would like to replace wherever X appears, right, we cannot replace with any of these vertices because they are forbidden. That is why in this in this disjoint feedback vertex set, we are only able to apply reduction rules to eliminate degree 2 vertices for certain kind of degree 2 vertices, not all kind of degree 2 vertices, right? And we will see that whatever elimination rule or whatever degree 2 reduction rule we have been able to apply, that is sufficient for us to make progress in the branching algorithm that I am going to explain next. Okay. So let's look at how the world looks like. So the world looks like very interesting. Here is my W, and this is also some forest. Okay. Here is my H. Okay. Now, since H is a forest, what can we say? There exists a vertex, okay? There exists a vertex X in vertex set of H of degree at most 1, okay? Now, let us say this is the vertex X of degree at most 1. Now, ask ourselves, where are its neighbors? Okay. Look, since we have applied, there is no vertex of degree 1 in this graph, it has at least one neighbor, and since its degree is 1 in H, its other neighbor must belong to some vertex in W. So, suppose it has neighbor some Y. Great. Now, let us ask ourselves a following question. But why it has only one neighbor, right? It has degree say exactly equal to 1. So, now but if this is how it looks like, then why did we not apply the reduction rule 2, reduction rule 3, which takes care of these kind of degree 2 vertices? That is because X has at least one more neighbor, right? X has at least one more neighbor, okay, somewhere, okay. So, now there are two questions. Can this X has another neighbor in the same component, okay? Can X have neighbor in same component as X is, as Y is? Well, no, because suppose I had this Z, then what is the property? Then look at the graph induced on W union X, it has a cycle, right? Rule 2 applies. Okay. So, the world is slightly different. Copy. Okay. So, this situation cannot arise. Okay. Okay. So, where is other neighbor? It must be somewhere in other component. Okay. So, now on this kind of vertices, I would like to branch. Okay. So, how will I branch? Okay, correct. Let us do branching. So, what is my branching? X belongs to my F, X does not belong to F. So, if X belongs to F, K drops by K minus 1, K drops by K minus, but what happens in this case? In this case, all I know that X moves to W. But if X moves to W, what happens? Nothing much can I say, right? Nothing much can I say. That all I know is that you have increased the number of vertices that what is that called? Which are forbidden. But there's something interesting happens actually. Okay, the something interesting that happens is then Okay, and this is something which people have exploited, is that when x moves to W, number of connected component in graph induced on W decreases. Okay, this is the, so in this case also something does decrease, and what is decreasing? Number of connected components of W. So the measure which I am going to use is K plus let us say gamma of W, or let us say gamma of okay, where what is this? Number of connected components of W. In the beginning, what is the measure? Is at most upper bounded by K. How many vertices are there in W? K plus 1. So number of connected component is upper bounded by K plus 1. So this is great. But intuitively, you must ask yourself, I mean, yes, we are making a progress, but then what happens if there is only one connected component? What happens if the number of connected component is exactly equal to 1? Then the number of connected component is not going to decrease, because number of component, right? Then if you notice, what happens is that this is just one connected component, and look at a vertex which is still, you will, because you cannot apply reduction rule, you will still find a vertex x who will have at least 2 neighbors there, but now these neighbors are in the same connected component, and hence all the neighbors of x will be in same connected component, and hence rule 2 will always apply, right. So this is just, this is not required for the proof, but this is just for your sanity check. This is for your sanity check. This is just for your sanity check, right. That a natural question that do arise is that, fine, oh, it's great that we are making a progress when the number of connected components are decreasing. But what happens when the number of connected components do not decrease? So in the moment you reach that stage of the algorithm, then you can solve the problem in polynomial time just by applying reduction rule 1, 2 and 3. Okay? So either what can happen, that reduction rule 1 applies because you can remove degree 1 vertices and W finishes, then you have an empty solution, or either or every time, because there is only one connected component, right. And notice that because this measure, okay. So now that we have introduced a measure, important point to notice is that measure mu does not increase by applying rule 1, rule 2 and rule 3, right. Because what was rule 1? Remove degree 1 vertex. When if you remove degree 1 vertex, the number of connected component cannot decrease, right. It can, like, it cannot increase. Number of connected component cannot increase by deleting a degree 1 vertex. By deleting a vertex in X, the number of connected component in W will not decrease. Similarly, if I look at the degree 2 vertex, the way we were making this edges, those also will not decrease the number of connected components in W, okay, which implies, right, that the mu does not increases the mu does not increase by applying reduction rule 1, 2 and 3. So this is very important, that whenever you have a branching algorithm, whenever we have branching algorithm, we ensure that measure does not increase either by branching rules or by reduction rules. Okay. So now what is happening? Okay. So now algorithm is very simple. Okay. Algorithm is very simple. Okay. Applies rule 1, 2, 3 exhaustively, picks a vertex of degree at most 1 in vertex set of H and branches on it. Okay. How? So suppose I have, so what are the branches of this? FVS of G minus X W K minus 1 or FVS of G W union X comma K. Okay. And in both cases, what is this? So in both cases here K drops. So look at, so I can think K and mu of I, right. So in this K drops by 1, mu of I remains same. Here K remains same, mu of I becomes less than 1. Okay. So now what did I use? Mu of I? No, I use gamma of I, sorry, right, number of component. Okay. And right, and here, right. So in the beginning we have this. So what is the change in measure? K minus 1 minus plus gamma I, right. Right. So this is what the major change is. So this is, the drop is equal to 1 in this case, and in the second case what happens is that we have K minus gamma I minus K but minus 1. So this is change. So which implies the running time of this algorithm is given by T of mu is 2 times T of mu minus 1. So the algorithm runs in times 2 to the power mu n to the power big O of 1, and mu is like how much? We just got an upper bound in mu is like 2k plus 1, right, here. Mu is upper bounded by 2k plus 1. So what do we get? Which is same as 4 to the power k n to the power. Okay. One thing I did not tell you is that here we said, oh, look at a vertex of, but we are only looking for a vertex of degree at most 1, right. Right. So you could also have a vertex of degree 0. If you will have a vertex of degree 0, then where are its neighbors? Then it's easy to see that its neighbors are, it has at least 2 neighbors for sure we know, and they must belong to 2 different components, because otherwise if they belong to the same component, reduction rule 2 would have applied again. Okay. Right, or here, right. Otherwise you can just branch on this vertex, call it Q, same way as you have branched on X, right, because either Q goes into the solution or Q moves to W and reduces the number of connected component by 1. Okay. So that kinds of completes my algorithm. Algorithm was fairly simple. Algorithm just applied some 3 reduction rules. Okay. Algorithm just applied reduction rule. right? Step 1 and step 2, and after applying the reduction rule, it picked a vertex of low degree, like degree at most 1, and branched either by putting this in the solution or not putting in the solution. But we saw a very interesting measure or interesting way to analyze the running time of this algorithm, which decreased the measure in both the branches, leading to an algorithm with running time 4 to the power k. Now, by using general methodology, what do we get? We get 5 power k n to the power big of 1 time algorithm for feedback vertex set, right? Right. So, what we have been able to get is a 5 power k n to the power big of 1 time algorithm for feedback vertex set using this, because remember we said that if we can get an alpha to the power k algorithm for disjoint version, then 1 plus alpha to the power k time we can get an algorithm for a feedback vertex set. Okay. I still have some time and I wanted to give you some algorithm other than this. Okay. So, I want to give you an algorithm for a different problem. Okay. So, the different problem that I would like to teach now is say 3-hitting set. Okay. So, what is a 3-hitting set? Input is universe, a family, an integer k, parameter k, and what is is a okay. So, I'll write it down, and f is a family of u of family of u. F is a family over universe u over universe u of size at most 3, right? And the question is, does there exist a set S subset of u? First, its size is at most k, and secondly, for every f in curly f, let us say curly f, okay, f intersection S is not equal to empty set, not that is S is a hitting set, right. So, you are given a universe where each an universe and a family, in a family there are each set is of size 3 or less, no more than that, and so clearly 3-hitting set has an algorithm. What is a simple algorithm? Here is my simple algorithm, branching algorithm. First, let f in, so in the beginning suppose S is empty set, let f in f, okay, and let f in f, okay, let f in f, okay, and a, b, c be its element. Then what I am going to do? 3-hitting set, okay, u okay, I will write it down, f a comma k minus 1, okay, or 3-hitting set u f b k minus 1 or 3-hitting set u f c comma k minus 1, okay. And what is f d? D belongs to a, b and c, is that from the family remove all sets that intersect D, right? So basically I have looked at FB. Now that I have decided that I am going to select A into my solution, okay, what I do, I look at the family. Now that I have decided that A must belong to my solution, then I remove all the sets that are already, that contains A, because those are already hit by A, so you don't need to hit any more, so that it reduces the problem of hitting the new family FA. Now, so what is this, what this algorithm will run in time is, so this algorithm is going to run in time 3 power k n to the power big O of 1, right? So each of time you call this, and like in the beginning it was, yeah, so this is a, if you're looking for a decision version, you don't need any S or something, you can just run this algorithm and you're very happy. Now what I'm going to do, I'm going to apply a compression version of this. So look, it's not a graph, but the compression is, so how will you apply compression version for this, right? It's not a graph, so we still will do the same thing. Suppose you have universe is like V1, V2, V1. Okay. Rather, you will see a different strategy here. Okay. So, here is my family F. Suppose it contains the sets F1 to Fm over U. So, now what I am going to construct, and U is U, U is U. I am going to construct family Fi is some first Fi sets. Okay. Now, my instance I is going to be U comma Fi. So, now notice, so I will run I1, I2, Im. Okay. This is how I am going to run my compression algorithm. Notice that if it says me no, at any point of time, if it says me no, right? If it says me no, what do I know? If it says me no, what do I know? If it says me no, then I know that U comma F comma K is a no instance, right? Because if you can't even hit small subset of family with K elements, what can you hit with, how can you hit all the sets, right? Okay, so this is exactly like the way we have been doing for vertex cover or feedback vertex set, so this is perfectly valid reason. Okay. Now what happens? So suppose we don't get into no, so what happens? Then we are going to get I1 and some set S1, I2, but what do I know about, right? Then go get to S2, so on and so on. Look at II, right? Si and look at II plus 1, right? Now what I know, Si intersects all the sets in II, right, or all the sets in Fi, right? It intersects all the sets. Now, but what is Fi plus 1? Fi plus 1 is actually nothing but is Fi plus 1 set, right? So what could happen? Okay, either Si intersects Fi plus 1 also, or we can get K plus 1 set intersecting every set in Fi plus 1. How? Add an arbitrary element from Fi plus 1 to Si, right? That's it. That is it. Okay. So this is how we can get to a compression problem. Now let's see how we can solve the compression problem. Okay. So what is our compression problem? Compression problem is exactly the same way. Compression 3-hitting set. Okay. What will the compression 3 heating set problem? Input is going to be u, f, an integer k, a set S of size k plus 1 such that S is a 3 heating set, is a heating set, is a heating set for F. Okay. And I am assuming from now onwards that all sets in F has size at most 3. Okay. Do not I am not going to repeat it again. Parameter is k, and the question is parameter is k, and the question is, does there exist a set H subset of U of size at most k, okay, of size, does there exist set H subset of U of size at most k such that H is a heating set for U comma F. Okay. This is a compression 3 heating set problem. Now, how do we get to a, let us say, disjoint compression 3 heating set problem? Okay. Disjoint compression 3 heating set problem. How? So, let us, we will get to that problem in a minute. Okay. So, to get there, what we used to do? We said, okay, let us, from here, we said, look, you gave me an S, okay, you gave me an S, I guess a set, I guess a Y, okay, I guess a set Y, which is going into my solution, right, which is going into my solution, okay, and then what should I do? Right. So, for graph problem we just deleted y and then okay, solve the remaining problem on the remaining graph. But here what will I do? I have decided to put y. So, what I will do, I do not care about y, but now given a family f, okay, I will make new family f tilde, remove every set that intersects y. So, every set that any element of y is being able to take care of, you delete it. So, you only keep those sets in f tilde who needs to be hit, that is it. So, this is how you can get a compression disjoint version of the problem for 3 heating set. Okay. So, it is not like graph, but it is more or less like a graph. So, what is the disjoint version of the problem we will get? We will get input U, F, K, F, mod S is at most some k plus 1 and F is a heating set, my parameter is k, question, does there exist a heating set of size at most k, does there exist a heating set H such that A, K, B, H is a heating set, phi H intersection S is empty set. Okay. So, now let us look at what happens to this problem. Okay. So, here is my algorithm, very simple algorithm. I said fine. So, look at a set. Okay. This is my some family F, there is an A, there is a B and there is a C. Okay. What is our sanity check algorithm? What is our sanity check? Sanity check. Sanity check is if there exists F such that all its elements are in S, say no, right? Because no way we can hit this F, right? No way we can hit this family because there is an F where all the elements are forbidden to be part of my solution. Okay, so no such F exists. No such F exists. Okay, but then let's look at what is the property of such. Okay, so here is my property. So now look at this is my F. There is some A and B and C. What I know, at least one element of this belongs to, say, S. Where does it belongs to? Because my S is my hitting set, this must belong to S. At least one, maybe more, but at least one element definitely belongs to S. So now I am going to create a family F tilde. What is my new family F tilde? It is F minus S for all F in F, right? And what is the property of this? Okay, so now each Fi tilde in F or each F tilde, what is the property? The size of F tilde is at most 2. So what has happened? So we were looking for a 3-hitting set problem, but in the compression step, we have got down to an algorithm, got down to a problem where each set has size at most 2. Because look, whatever hitting set you are going to construct, it must hit the elements which are not allowed to be hit, like which are allowed to be hit. Not so. What you do, you construct a different family where the arity or the size of each set decreases by 1. Now, what is this problem? This is nothing but a 2-hitting set problem, right? And for 2-hitting set problem, what do we know? This is same as vertex cover. In fact, so of course, if there is an element of size, if there is a set of size 1, you definitely have to put them into a solution, move them off. So each set has size exactly equal to 2. Then you can think of a graph where graph on U and each set will correspond to an edge. So this is exactly vertex cover problem. And for vertex cover, you must have seen a very good branching algorithm in your lecture on branching. And what was that algorithm? At least one algorithm I can tell you. Find a vertex or of degree greater or equal to 3, right? So if you have a vertex of degree greater than or equal to 3, right? You, in one branch, you include U in the solution, in the other branch, you include NU in the solution, leading to the following recurrence: T of k is less than or equal to T of k minus 1 plus T of k minus 3, leading to 1.456 to the power 5k algorithm. And when there is no vertex of degree 3, so or maximum degree of the graph is at most 2, solve the problem in polytime. Solve the problem in polynomial time. Okay. So now we know such a good algorithm for vertex cover. So the vertex cover algorithm we know is 1.4565 to the power k. So now if I do my computation, right? So what is the disjoint algorithm will take? It is going to be summation k plus 1 choose I, right? 1.456 to the power 5 k minus I. And if you do the computation as we have done before, we have got an algorithm with running time roughly n to the power big O of 1 for 3-hitting set. Right. So we have got such an algorithm. So we started with a 3 to the power k algorithm, but in the comparison step, we reduced this problem to a 2-hitting set problem, and we employed the fast algorithm for 2-hitting set to get a fast algorithm for 3-hitting set. So I think that's all that I would like to talk about in this lecture, and we might have one more lecture on iterative compression.